Oh, good day. This is Chris with the Ancient Scholar. And today, what I'd like to talk about is I'd like to go ahead and talk a little more about the transition metals and talk about some theories of bonding that are kind of associated with these transition metals. So first of all, let's just throw this up. Transition metal. All right, transition metals. All right, these are metals found at the center of the periodic table of elements, and we just finished a video. I just finished a video talking about the electron configuration of transition metals, and what makes transition metals is the fact that when these metals, so when these metals are ions. Okay, when they're ions, they have partially filled d orbitals. All right, partially filled d orbitals. In fact, when these guys are metal ions, the d orbitals, okay, the d orbitals are the valence shell. All right. So let's just talk about this real quick. So let's just say, let's do iron. Okay, this is a very common thing. So let's do iron. There's iron. And if you remember the electron configuration of iron, okay, it's argon. All right, so if argon here, and it is 4s2, okay, 3d6. All right, so that's the electron configuration for iron. And so we know that metals tend to lose electrons, and that's what makes them ions. And transition metals can have different ions. Okay, they have different ions. If you look at sodium, for example, really the only sodium ion of any significance is the Na+1, because if you remember sodium, okay, sodium has one electron, and if it loses that electron, then the shell underneath is full, has a full octet, and it can be the new valence shell. There's something a little different going on with transition metals. Transition metals can have different ions, and when we talk about transition metals, okay, we talk about the chemistry of transition metals. There is a term that's very important, and in the context of transition metals, this term actually has different types of contextual understanding associated with it, but we're just talking about transition metals. This term is known as the oxidation state. Okay. And the oxidation state is just a way of saying what is the ionic charge. Okay, so when we talk about the sodium ion would have an oxidation state of +1. That's all I'm saying there. But the transition metals can often have several or multiple oxidation states. So, for example, iron. Okay, iron. Let's get rid of that there. Iron has two common oxidation states. So the two common oxidation states of iron are Fe +2 and Fe +3. Okay, so that means that that's iron that has lost 2 electrons or lost 3 electrons. Okay, so if we were to look at the electron configuration of iron again, we would have this. Okay, so we have the 6 electrons in the 3D shell and 2 electrons in the 4s. And we know that the 4s shell has a slightly higher energy. Okay, so I'm going to put my 4s here, and then I'm going to put my 3D down here at a slightly lower energy. And there are 5 d orbitals, if you remember. So 1, 2, 3, 4, 5. Okay, and then so these are the 3D. So I've got 2 electrons. So 1, 2 electrons here. And then I have 6 electrons. So using Hund's rule, we'll go ahead and put our electrons in the 3D shell. 5 and then 6. Okay, so this is what iron looks like, the elemental iron. So if I want Fe plus 2, what I have to do is I have to remove 2 electrons. And when we remove electrons, or when we ionize something, the outer electrons, the electrons with the highest energy, are removed first. So that would be the s electrons. So in iron, we will remove these 2 electrons. So in this case, this is what the Fe plus 2 ion would look like. Okay, and then those 2 electrons that we lost were from the 4s shell. Okay, but let's talk about Fe plus 3 now. So let me go ahead and repopulate the 4s orbital with electrons. So iron 3, or iron with an oxidation state of 3, we're going to need to take 3 electrons. So we'll go ahead and take our 2, and then what happens? Well, then I have to take electrons from the next shell, okay, which is going to be the 3D, and it'll be this electron here. So this would be what the valence configuration of Fe plus 3 would look like. Okay, so that's kind of how iron is just one example of transition metal, but obviously there are many other examples we could use, but iron is something we all know, so that's something we can use. Okay, so that's one interesting thing about transition metals, is that transition metals are metals, so they tend to lose electrons. They tend to have partially filled d orbitals, which is very important. And they have your general metallic characteristics. And the metallic characteristics are things like conductivity. Okay, they can conduct electricity very well. Why? Well, because they have these partially filled d orbitals, and electrons can move in and out of those d orbitals very easily because they're partially filled, and that allows many of the metals to conduct electricity. Metals are also really good at a type of bonding known as metallic bonding. Okay, and where you can have, so if this is let's say that these are iron nuclei, and the tendency is for, if you get a bunch of iron together, for example, the nuclei can kind of delocalize themselves, and of course the nuclei are all positive, and because you have all these partially filled d orbitals and all these electrons kind of everywhere, the electrons kind of are just kind of create a soup, or kind of an ocean of negative charge around the positively charged iron nuclei. So what does that mean? That means that the electrons are attracted to the nuclei are attracted to electrons, and it kind of holds itself together and this, makes our metal, a block of iron, it's very strong. Okay, but because this is kind of like an ocean or a soup of electrons, it can be bent. You can bend it. Okay, this is not like sodium chloride, right? An ionic bond, which creates a crystal like salt crystals, where you can't bend salt crystals; they tend to break. But metals you can bend because you have this sea of electrons that these positive nuclei are kind of floating in a way. But they're very strong. They hold together really well. They're bend. We call that malleability. They have very high, for the most part, they have very high melting. Okay, they have very high melting points, and they're very good at conducting heat. Okay, they're very good at conducting heat. Is able to move through these very well. So that's just these are some of the unique properties of these transition metals. Okay, when we look in general, I'm going to look at just the first row, okay, of the D block, in specifically, and that includes the scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. Okay, and when we look at those, starting from the left-hand side of the periodic table over to the right-hand side. So as I move from left to right, what are some things that I can expect? Well, I can expect, in general, I can expect the 2+ ion to increase in stability. All right, so the 2+ ion, the 2+ oxidation state, will become more and more stable as I move from left to right, as I move from scandium over to zinc. Okay. However, as I move over from left to right, of course, there are more and more protons in the atoms, and so what that means is that those atoms are not going to like to have a whole lot of electrons taken away. 2 electrons, not a big deal, but the maximum oxidation state, okay, as I move from left to right, is generally going to be less stable. So transition metals that have very high oxidation states are going to be highly reactive because they're going to want to get a hold of electrons, and that's going to make them highly reactive. In addition to that, as we move left to right, their tendency to form what are called complex ions, okay, and I'll put that in parentheses because that's going to be something that I'll be talking about in detail, to form complex ions with something called a ligand. Okay, if you've never heard of that term, don't worry, because that is something that I'm going to talk about in detail later on. But their ability to form complex ions with ligands increases. All right, their ability to do that increases. Okay, and many of the ions, okay, tend to form cool colors. All right, these things can be very colorful. They can take on lots of blues and violets and reds and so on and so forth. Okay, it is worth just kind of throwing in the back of your mind that there are some ions that don't form colors, and it is specifically the copper. So Cu+1 does not tend to form bright colored ions, and the reason being If you look at the electron configuration of Cu plus 1, it's like this, 4s, that's argon, and it has a 4s1, 3d10, okay? So the plus 1 configuration of copper, you're going to lose the 4s electron, and you're just going to have a valence configuration of 3d10. Remember what we said, a transition metal has a partially filled d orbital, but in this case the d orbitals are all full. So Cu plus 1 is not really a transition metal. All right, so it's not going to form those bright colors that you would expect with other transition metals, and it won't have some of the other properties that we talked about. The other one that's kind of the exception as well is going to be the zinc plus 2 ion. Okay, so if we look at the electron configuration of zinc, that's going to be argon. Okay, let's see, 4s2, 3d10. So you can see that the plus 2 ion, I'm going to lose my 2 s electrons, which will leave me with a full d, all my d orbitals full. So again, zinc, its plus 2 ion is not really a transition metal either. Other ions, though, can have other properties, but those are just kind of some noteworthy things there. Okay, another thing that you really want to know about the transition metals are really good, okay, catalysts. Okay, very important to know that. We use the heck out of transition metals in industry to catalyze chemical reactions. These are very good catalysts, and we'll talk a little bit about that. Let's see if I can throw out some examples. I know one example is vanadium V2, vanadium oxide V2O5. Vanadium oxide is really important in catalyzing some of the reactions for creating sulfuric acid. All right, that's one example of vanadium being of a transition metal being an important catalyst. Let's see here, manganese oxide, MnO2, I believe, is a really good catalyst for creating oxygen. Chemical reactions create oxygen, obviously, oxygen there. And there's a whole laundry list, but bottom line, transition metals are really good catalysts. They're also very good catalysts in biochemistry. All right, so in chemistry within the body, and they are very important in enzymes. And an example of a transition metal being critically important in an enzyme would be something like hemoglobin. Okay, where you have iron. Okay, you have iron, and iron acts as a catalyst in the overall transport and delivery of oxygen. Oxygen is able to coordinate itself with iron in hemoglobin. So that's just yet another example of how critically important these transition metals are. Okay, so let's talk about transition metals and how they can form what we call complexes. They can form complexes with what are called ligands. All right, form complexes what are called ligands. Ligands are simply molecules, or in some case they can even be atoms, that are able to donate. They're able to donate, okay, pairs of electrons, okay? And if you're able to donate a pair of electrons, another term for you is what's called a Lewis base. If you donate a pair of electrons, you're a Lewis base. If you accept a pair of electrons, you're a Lewis acid. So ligands are Lewis bases, and obviously the metals would be Lewis acids in this case. Okay, so these ligands are able to interact. They're able to interact with the metals, and that interaction results in something known as a coordination. Okay, a coordination complex. So basically, that is a type of bond, if you want to look at it that way. It is a type of bond. It is a way to bond. Now, we have talked about ionic, true ionic bonding. We've talked about covalent bonding. And I also have some videos on intermolecular forces, such as hydrogen bonding and London dispersion forces and whatnot. The coordination complex is a very special type of bond, and there are two theories out there that we can use to describe the coordination complex with transition metals. The first theory is something known as crystal field theory. All right, and the other one is known as ligand field theory. All right, crystal field theory was originally a physicist by the name of Hans Bethe, working with someone else, I don't remember the other person's name, came up with this in, I believe, 1929, 1930. And then it was followed a few years after that by ligand field theory. The only one that I'm really going to talk about is the crystal field theory. Crystal field theory is a bit more intuitive. It's a bit simpler, but it is not complete. It has some pitfalls, and really the ligand field theory is the more accurate way to go. It involves it actually involves hybridizing atomic orbitals, and it's a true quantum mechanical theory, where crystal field theory involves a different way of looking at it. But crystal field theory is still really good. It still makes some good predictions. It just doesn't work in all situations. And frankly, it's a lot easier to understand, however. So I'm going to focus on crystal field theory when we talk about coordination complexes and coordination chemistry. I think I'm going to go ahead and just cut it off here, and then I'll start a new video and we'll just go into crystal field theory and start working our way through that. Okay guys, hopefully that made sense, and as always, I thank you guys for hanging in there.